Symmetric Relations. Hello everyone. Today, we are beginning our discussion on symmetric relations. To start, let's look at the general concept. In the study of relations, symmetry refers to a specific property known as reciprocity. To put this in simpler terms, if a relation is symmetric, it means that the relationship holds true in both directions between any two elements. Essentially, if an element A is related to an element B, then element B must also be related back to element A. As we move forward in this lesson, we will transition from this intuitive idea to a formal mathematical definition, and then apply it to both real-world and numerical examples to ensure you can identify these relations with ease. Formal definition of symmetric relations. Now that we have introduced the general concept of reciprocity, let us move on to the formal definition of a symmetric relation. A relation, which we will denote as R, defined on a set A, is said to be symmetric if, whenever an element, let's call it a 1, is related to another element, a 2, it is also necessarily true that a 2 is related back to a 1. To express this mathematically, for all elements a 1 and a 2 belonging to set A, if the ordered pair a 1, a 2 is a member of relation R, then the ordered pair a 2, a 1 must also be a member of relation R. In simpler terms, you can think of this as a mirror image. If the pair a 1, a 2 exists within the relation, its mirror image, which is the reversed pair a 2, a 1, must also exist for the relation to be classified as symmetric. Having established this formal definition, we will now look at the logical steps required to determine if a specific relation is symmetric in our next slide. Conceptual breakdown of symmetric relations. Now that we have established the formal definition of symmetry, let's look at how we can actually apply this to determine if a given relation is symmetric in practice. To do this, you can follow these logical steps. First, you must identify the pairs. This simply means you should carefully examine all the ordered pairs, x, y, that are present in the relation R. Next, we check for reciprocity. For every pair x, y where x is not equal to y, you must verify if the reversed pair, y, x, is also present within the set R. Then, we handle the self-related pairs. You will notice that pairs of the form x, x are automatically symmetric. This is because reversing the elements results in the exact same pair, x, x, so they always satisfy the condition. Finally, we reach our conclusion. If every single pair in the relation R has its corresponding reversed pair also present in R, then the relation is symmetric. However, keep in mind that if even one single pair is missing its reverse, the entire relation is not symmetric. To help you visualize this process, we will now move on to a real-world example in the next slide. Real-world example, the sibling relation. Now that we have established the formal definition and the logical steps for identifying symmetry, let us move from abstract theory to a more intuitive, real-world scenario to see how this works in practice. Consider a scenario where we have a set, which we will call set A, consisting of all human beings. Within this set, we define a relation, R, as the relationship of being a sibling of another person. To analyze this, let us apply the logic we discussed in the previous slide. Suppose person X is a sibling of person Y in mathematical terms. This means the ordered pair x, y belongs to the relation R. Now, think about the nature of this relationship. If person X is a sibling of person Y, then by necessity, person Y must also be a sibling of person X. It is a relationship that cannot exist in only one direction. Therefore, the reversed pair, y, x, must also belong to the relation R. In conclusion, because the relationship is a sibling of always works in both directions, acting as that mirror image we mentioned earlier, it is a symmetric relation. This provides us with a clear conceptual foundation before we move on to verify symmetry using a purely mathematical set in the next slide. Mathematical example. Now that we have explored the intuitive concept of symmetry through the sibling example, let us examine a mathematical set to see how to verify symmetry formally. First, let's look at our given information. We have a set A which contains the elements 1, 2, and 3. On this set, we have a relation R consisting of the ordered pairs 1, 2, 2, 1, 1, 1, and 2, 2. To determine if this relation is symmetric, we will apply the verification steps we discussed in the previous slide. First, let us examine the pair 1, 2. Its reverse or mirror image is the pair 2, 1. Since 2, 1 is present in our relation, this pair satisfies the symmetry condition. Next, we examine the pair 2, 1. Its reverse is 1, 2. Since 1, 2 is also present in the relation, this pair also satisfies the condition. Now let's look at the self-related pairs. As we mentioned in our conceptual breakdown, these are automatically symmetric. For the pair 1, 1, the reverse is simply 1, 1. Since it is present, it satisfies the condition. Similarly, for the pair 2, 2, the reverse is 2, 2. Since it is present, it also satisfies the condition. In conclusion, since every single pair in relation R has its corresponding reversed pair also present in R, we can formally state that the relation R is symmetric. Keep this process in mind, as in the next slide, we will discuss some common mistakes students make when performing this type of verification. Common mistakes. Now that we have seen how to verify symmetry through real-world and mathematical examples, let us address some common misconceptions that students often encounter to ensure you avoid these pitfalls in your exams. First, it is very common to confuse symmetry with reflexivity. A frequent error is believing that every element must be related to itself, for example, the pair 1, 1, for a relation to be symmetric. However, this is incorrect. While reflexivity specifically requires that every element is related to itself, symmetry only requires that if a pair A, B exists, then its reverse, B, A, must also exist. In other words, a relation can be perfectly symmetric even if it is not reflexive. Next, let us discuss the concept of non-existence. Some students assume that if a relation contains no pairs at all, which we call the empty relation, it cannot be symmetric. In reality, the empty relation is considered vacuously symmetric. This is because the condition for symmetry is never violated. There is simply no pair A, B present that fails to have a corresponding reverse pair. Finally, be careful not to overlook a single pair. When dealing with a large set of ordered pairs, it is tempting to check only a few and assume the entire relation is symmetric. Please remember that symmetry is a universal property. If even one single pair A, B exists without its mirror image B, A, the entire relation is classified as non-symmetric. Keep these warnings in mind as we move toward our final key takeaways in the next slide. Key takeaways. Now that we have covered the definitions, examples, and common pitfalls, let us conclude this lesson with the key takeaways to ensure you have a solid grasp of symmetric relations. First, remember the concept of reciprocity. As we discussed with the sibling example, symmetry is essentially a two-way street. If a relationship exists from one element to another, it must also exist in the opposite direction. Moving to the formal condition, this is expressed mathematically as: if the ordered pair A1, A2 belongs to the relation R, then it must follow that the ordered pair A2, A1 also belongs to the relation R. This is the mirror image property we examined earlier. Regarding verification, keep in mind the two different approaches. To prove that a relation is symmetric, you must be thorough and show that for every single pair present in the set, its reverse also exists. However, to prove that a relation is not symmetric, you do not need to check every pair. You only need to find one single counterexample, which is a pair whose reverse is missing from the relation. Finally, it is crucial to understand the independence of these properties. As we noted in the common mistakes slide, symmetry is independent of reflexivity and transitivity. A relation can be symmetric without being reflexive, and vice versa. Each of these properties describes a different characteristic of a relation.